All right. Before we get going, I just want to note on the participation questions for today. I didn't actually finish the question on question number 3. It's supposed to be asking which of the 2 following solutions is more acidic. And I just asked which of the following point molar solutions, and then is nothing. Like it didn't finish the question. So question number 3 is asking which of those 2 solutions is more acidic. Okay. That's what it's trying to ask. So again, for question number 3, which of the following solutions is more acidic? Okay. Again, just a reminder, which is more acidic is for number 3. All right. Otherwise, are there any questions people have before we get going today? Anything that was maybe covered on Monday? Anything in general about the course? Acid, bases, pH, strong acids. Going on Zoom here. All right. So in that case, we'll go ahead and get going. So we left off last time talking about our strong acids. Talked about right, that the strong acids completely dissociate, right, to produce protons and some anion, some spectator ion in solution. Okay. Okay. And so now talking about strong bases, right? So what will a strong base do in solution? Similar to what a strong acid does in solution.
Dissociates.
Yeah. So a strong base will fully dissociate in solution. We go to, where's that at? Right, so strong base fully dissociates in solution. So for example, an example of strong base NaOH fully break apart into Na plus and OH minus. Okay. Right, so a strong base, right, is considered a strong base because it fully breaks apart in solution, right? Something that doesn't fully dissociate is a weak base or a weak acid, right? If it's a base or an acid, right? So strong acids, strong bases fully break apart in solution. Okay. So your strong bases and strong acids are basically your group 1, group 2 hydroxide. Okay, or not strong acids, right? But your strong bases are your group 1, group 2 hydroxides, sodium hydroxide, potassium hydroxide, lithium hydroxide, so on and so forth, right? Magnesium hydroxide. The strong group 1, group 2 heavy metal hydroxides are your strong bases. All of their bases are going to be a weak base. Okay. Right. So just like strong acids, right? You just need to kind of know what they are. Strong bases as well. Okay. There aren't that many of them, so it's not too difficult to memorize, right? And if something's not on our list of strong acids or list of strong bases, then it is a weak acid or weak base, right? Right. And so, right, for strong acids, we knew that the concentration of the acid equaled the concentration of hydrogen ions introduced in solution. It's similar here for strong bases, at least for the group 1 bases, because for the group 1 bases, you just have one hydroxide, right, per molecule. This ionic compound, sodium hydroxide, just has one hydroxide, so it breaks off into sodium and hydroxide ions. But for your group 2 hydroxides, right, you have 2 hydroxides per base, right? And so for every 1 calcium hydroxide, I get 2 hydroxides in solution, right? So the hydroxide concentration in solution, OH minus, right, is 2 times the concentration of that base when it got placed in solution. Okay. Right, so if I have a 2 molar calcium hydroxide solution, right, the concentration of hydroxide is going to be 4 molar, right? It's going to be twice the concentration of calcium hydroxide. Okay. So questions about this? Strong bases. Right, our strong bases and strong acids are kind of the easier things to work with, okay? Is again, getting the pHs of those solutions, right, is fairly straightforward because it's just going to be related with the concentrations of the base or of the acid, right, because these things fully dissociate and completely break apart. All right. So let's pretend I have a 0.25 molar solution of sodium hydroxide. Let's find out the pH of that solution. So wait a second. Right, it's on the handout here. Right. Wait a minute here for people to try to calculate the pH on their own. Then we'll do that together. Right. And we're going to do example number 2, or like the example right below that, pH of strong base 2, right? Right after this. So if you want to work on both of them, you're welcome to. All right, so we want to find the pH of these solutions, right? So I have a sodium hydroxide solution, right? So in solution, that's a strong base, so it completely breaks apart. The sodium ions plus hydroxide ions. So if I start off with 0.25 molar sodium hydroxide, what's the concentration of my hydroxide ion? And what's the concentration of OH minus here, the hydroxide? If 100% of NaOH dissociates, what's going to be that final concentration of sodium hydroxide, or of hydroxide, sorry?
Is it 0.25?
Yep. 0.25 molar, right? This thing fully breaks apart. So if I start off with 0.25 molar sodium hydroxide, right, this will form 0.25 molar OH, right? So I know I have 0.25 molar of OH in solution, because again, this I draw this as an arrow just to the right on purpose, right? That there is no equilibrium here. This reaction, right? This dissociation of sodium hydroxide into sodium and hydroxide ions goes to completion. So every last mole of sodium hydroxide breaks apart to form equivalent amounts of moles of sodium ion and hydroxide ion. So I have 0.25 molar hydroxide, right? And I want the pH, right? How would I calculate the pH normally, right? What is that formula for calculating the pH? pH equals, here's some negative logs. Negative log of what? Right?
0.25.
H plus ion concentration, right? So this is what I want, right? I want the pH, negative log of H plus ion concentration. Now, I don't have that, right? I have the hydroxide ion concentration, okay? Now, there's two different ways I can get from OH minus concentration to pH, right? This is concentration of OH minus, right? So there's two different ways I can get from that OH minus concentration to my pH. Either way works. Either way will give you the correct answer, okay? You don't have any thoughts about what I can do from this point, right? I have the concentration of OH minus. I need to get to my pH. What might I do to try to get there?
Take the pH of the hydrogen and minus it from 14?
POH?
Yeah, so yeah, I think you're looking for the POH, the P of hydroxide, right? POH, and take that from 14. And then in class here, there's a question, or?
Yeah, I have a question.
Yep.
I'm kind of confused on why they use the H plus, not the OH right there, like the negative log.
Well, so this is just the definition of the pH. pH is defined as the negative log of the H plus ion concentration, right? And so it's just, right now, I don't know what that is, right? I introduced a base, there's an OH minus, concentration of 0.25, okay? And so, yeah, so one of the suggestions over Zoom, right, was the fact that I know the pH plus the POH equals 14, okay? That's one of those equations talked about last time, right, where the POH, right, is just equal to the negative log of the OH minus concentration, right? And so yeah, so I can do that, right? So I can calculate the POH, and then I can do 14 minus POH to get my pH, okay? You want to know the other way you can get to the pH here? What other relationship do we have that relates OH minus and H plus concentrations.
H plus times OH minus equals 1 times 10 to the negative 14.
Yep. Right. So we know, right, this is in a solution of water, right? Every acid-base reaction we're going to talk about in this class is always assuming the solvent is water, right? And in water, there's that auto-ionization reaction that's always occurring. That's an equilibrium reaction that tells me in every solution of water, concentration of H plus times concentration of OH minus always equals 1 times 10 to the minus 14. Okay, 4 there. Right? So always concentration of H plus times OH minus equals 1 times 10 to the minus 14. So I can plug in for the concentration of OH minus here of 0.25, divide that over, solve for the concentration of H plus, plug that into there to get my pH, right? Or again, I can use my concentration of OH minus to solve for my pOH, plug that in into here, and solve for my pH. Again, there's 2 different ways you could do this. Either way will give you the exact same answer. Okay, just whatever you prefer to do. I often calculate the pH and then the pOH and then convert that to the pH using the equation above, just because I feel like the math is simpler. Might not be, but that's how I feel about it, right? So if I want to do that, right, I get the pOH. Okay, take the negative log of 0.25. Okay, and you get this as 0.60. And so the pH is 14 minus that, which is 13.40. So the pH of this solution of 0.25 molar sodium hydroxide is 13.40. Okay. Again, I got from the pOH to the pH by using this formula up here, right? I did 14 minus the pOH, so 14 minus 0.6 gives me 13.4. Okay. Yeah, question? By taking the negative log of 0.25. So the pOH here is the negative log of 0.25. And that comes, if I did my calculations correct, that comes out to be 0.6. Right. Okay. All right, for this example number 2, I'm going to okay. So this is strontium hydroxide, okay? And again, I start off with a 0.25 molar solution of that, okay? Again, wait just a minute. People to attempt this problem on their own, right? Given how we did the previous problem, right? In the guide, right? Try to work this out on your own. And then we'll work it out together. All right, so right for this strong base, right, this breaks apart, SR2 plus 2 OH minus, right? And so if I start off with a 0.25 molar solution of strontium hydroxide, when this fully dissociates, what is my final concentration of OH minus in solution? And this 0.25 molar completely breaks apart.
The double?
Yeah, so it's double the 0.25, so it's going to be right 2 times 0.25, which is 0.5 molar, right? So 0.5 molar is concentration of OH minus here in solution, because again, right, every 1 mole of strontium hydroxide breaks apart into 2 moles of hydroxide, right? Based off the balanced chemical reaction here of this thing fully breaking apart. Okay. So we have now a solution of 0.5 molar hydroxide, right? So again, I can use these formulas, right, to get my pH, okay, by either first calculating the H plus ion concentration, then taking the negative log of that, or finding the pOH, right, the pOH equal to the negative log of OH minus concentration, right, which is going to be negative log of 0.5. The pOH comes out to be 0.3. Okay. And so then to find the pH, I have, right, the pH plus pOH equals 14. So that means pH equals 14 minus the pOH, which is 0.3. So my pH is equal to 13.7. Okay. Which again, you could get to by doing 1 times 10 to the minus 14, divide that by 0.5, okay? All right, which will give you 2 times 10 to the minus 14. And if you take the negative log of 2 times 10 to the minus 14, you'll get 17.3. Okay. So yeah. Again, it's completely up to you as to how you solve for the pH. Okay. But either direction you go, you will get the same answer. Okay. So questions about these 2 examples? Okay. You have plenty of examples like this on the homework and things of that nature. But I, again, strongly recommend going over lots of these examples so you get very comfortable of calculating the pH once you know concentrations of H plus ions, like in the example up here, right, versus concentration of, say, OH minus ions in solution, right? Because this will be something that's going to be happening plenty in this class over the next few weeks, okay? So we should get very comfortable, very familiar with doing these types of problems, okay, so that they start to become second nature as we go through this chapter and chapter 17. Okay. So again, right, the equations up here, right, are also given in the slides last time. I'll go back to slides, right? And these, it's also posted, right? These lecture slides are posted online. These equations, right? Become familiar with them. You'll use them often. Okay. All right. All right. So another question here. What is the pH of a solution which has a concentration of OH minus equal to 8.9 times 10 to the minus 9? And you can do A, 5.95, B, 7, C, 8.05, or D, 14. All right, so on Zoom here, got some people saying A. So this question, you can definitely go out and calculate the pH, right? By say calculating the pOH and then doing 14 minus the pOH. Okay, you'll get one of these answers. But we can also reason out the answer based off of the possibilities that we're given, right? Without ever having to plug anything into a calculator. Okay, I know, for example, B here, a pH of 7 is for a neutral solution, which means the concentration of H plus and the concentration of OH minus equals 1 times 10 to the minus 7, which is not the concentration given. Okay, so I know it can't be B, right? And then I also know, right, the concentration of OH minus is 8.9 times 10 to the minus 9. Okay, that tells me my solution is what? Acidic or basic? It's going to be acidic, right? Concentration of this solution is going to be acidic, okay? Because again, a neutral solution has concentrations of H plus and OH minus equaling 1 times 10 to the minus 7, right? If one ink, and we know, right, for water, right, we have that auto-ionization reaction somewhere here, right? Right, we know we have this equilibrium established between H plus and OH minus, right? That the concentration of H plus times the concentration of OH minus always equals 1 times 10 to the minus 14. Okay, which means if the concentration of H plus increases, concentration of OH minus has to decrease, and vice versa, right? Concentration of OH minus, if that increases, concentration of H plus has to decrease. Okay, where again in a neutral solution they both start off at 1 times 10 to the minus 7, right? Again, neutral solution pH 7, 1 times 10 to the minus 7, concentrations of H plus OH minus. As I get to more basic solutions, my concentration of OH minus becomes greater than 1 times 10 to the minus 7, while my concentration of H plus becomes smaller than 1 times 10 to the minus 7. And then for acidic solutions, it's the exact opposite, right? For acidic solutions, I have a lot of H plus in solution, so its concentration is greater than 1 times 10 to the minus 7. And therefore, the concentration of OH minus has to be less than 1 times 10 to the minus 7, right? And so for this question, right? Oh, skipped it. Right, for this question, I know this solution is acidic because the concentration of OH minus is less than 1 times 10 to the minus 7, which means the concentration of H plus has to be greater than 1 times 10 to the minus 7. So it's an acidic solution, and the only pH here that is a pH for an acidic solution is A, 5.95. So even if I didn't have a calculator, I could figure out that the answer to this question has to be A, 5.95 by just understanding the relationship between H plus and OH minus concentrations in solution, and those relationships between pH and whether or not a solution is acidic or basic. Okay. Any questions about that and about how I can, without a calculator, figure out that the answer is A here? Yep. So if I had a solution of OH minus that was So repeat. You're asking if OH minus will always be basic, or so? Yeah. If the concentration of OH minus is always if it's greater than 1 times 10 to the minus 7, it's always basic, and if it's less than 1 times 10 to the minus 7, it's always acidic. Yeah. OH minus itself is a base. It's a proton acceptor, and so the more of that base you have, the more basic your solution becomes, right? And so, and then we just call a solution basic has a concentration greater than 1 times 10 to the minus 7 of OH minus. Yeah. But every solution, right, will have some amount of H plus and OH minus in that solution, right? It's just considered basic or acidic depending on the relative concentrations of those things. Okay. Other questions? All right, so now we're going to start talking about weak acids and weak bases. It's going to be a little bit more complicated finding the pHs of these guys. We'll do plenty of examples of that. Okay. Well, what would you suspect, right? The definition of a strong acid is a molecule that fully dissociates, fully breaks apart in solution, right? So what would you expect the definition of a weak acid to be? Yeah, something that only partially dissociates in solution, right? Only partially breaks apart in solution, okay? Right, so weak acid, something that right? So often for weak acid, what we'll end up having here is something like HA. Why can't I see the mouse here? Minus H plus. And general, right? Something that only partially dissociates, does not 100% break up. And so what will happen is you'll have some equilibrium established, right, between the weak acid and its conjugate base, right? It's going to be HA. Its conjugate base is going to be A minus. Okay, and that is going to have a equilibrium constant that we're going to call Ka here. Back here to insert an equation again. Right, which is going to equal what? What will Ka equal for this reaction given above? What is the equilibrium constant, right? Let's not, you know, we can pretend there's no A here, right? What is K, the equilibrium constant, equal to?
The concentration of A minus times the concentration of H plus over concentration of HA.
Yep. Right, that is the equilibrium constant for this reaction. And since it's an equilibrium reaction for a weak acid, we call it Ka. Okay, so that little A is just telling us this is a weak acid dissociation equilibrium reaction. Okay, that's all the A's there. It's just saying, oh, hey, this equilibrium constant is for a weak acid equilibria. Okay, right? But it's just an equilibrium constant K here, right? Right? And so, right, in terms of what are weak acids, right? Basically anything that isn't a strong acid. Again, it's a lot easier to know all the strong acids because there's way too many weak acids to ever try to memorize them, okay? But there's only a select few of strong acids, okay? So here I'm giving some examples of weak acids, okay? Hydrofluoric acid, chlorous, nitrous acid, okay? So here I want to just make a note on some of these acids like benzoic acid, acetic acid, okay? Right, that for example, for benzoic acid, okay, we'll often write the formula for this acid as C, you know, as like a bunch of stuff, than COOH. Okay. And the reason it's written like that is just to indicate kind of how the structure of the molecule looks like, where you have this carbon double bonded with one oxygen and then bonded with a different oxygen that has a hydrogen attached. Okay. And if you ever see this, just remember that this does not donate an OH to solution. That carbon-oxygen bond is not going to break. Okay. But what will break is the oxygen-hydrogen bond. Okay. Right. So this is an acid, not a base. Right. So just keep in mind, right, that things like benzoic acid, acetic acid, these acids where the H plus breaks off into solution, not some sort of OH minus. Okay. So again, these are weak acids that donate protons in solution. Okay, and not OH minus solutions. Okay. And that proton that's donated is typically written at the end of the formula here, okay, right, and not typically given at the front, right? A lot of these other acids like HF, HNO2, right, we write the acidic acid at the front, okay, HOCl, cyanide, right, HCN. Those things have the acidic acid written on the front of the molecule, but these carboxylic acids that have this type of structure will often write the formula as such, where the acidic acid is at the end of the molecule. Okay? Just kind of noting here that these are very common acids. We'll do plenty of examples, like with acetic acid and such. Okay, that CH3COOH. Okay, acetic acid we'll use quite a bit. Okay, so just keep that in mind that it is an acid that donates a proton, not an OH minus group. Okay. All right. So which of the following here is a weak acid? It's going to be hydrochloric acid, sulfuric acid, nitric acid, hydroiodic acid, or nitrous acid. So got some people on Zoom here saying D or E. All right, so let's chloric, sulfuric, nitric. All right, so the hydrochloric acid, okay, HClO4, right? Sulfuric acid, H2SO4, hydroiodic acid. Oh, that was D, right? Or was that? Shoot. Nitric acid and then hydroiodic. There we go. So nitric acid, HNO3, hydroiodic acid, HI, and E here, nitrous acid, HNO2. Okay. So this question basically is, did you memorize your list of strong acids? Because A through D here are all strong acids. Okay, they're all given in that list of strong acids earlier in the lecture, went over on Monday, and again in the lecture slides. Okay, E here is the only one that is not, so that is a weak acid. Okay. Near the end of this chapter, we'll talk about why, say, HNO2 is a weak acid versus HNO3 being a strong acid. Okay. But for now, just know that one is strong, the other one is weak. Questions about this example?
On an exam, will they be giving by name or by their chemical formula?
It's a good question. Typically, I will be giving them by the chemical formula. I'm trying to think. I've ever done that. I tend to Yep. All right. Okay. Sorry. Audio is back. Yeah, I don't know. It just randomly does that. Right. So in Ka here is the equilibrium constant for some weak acid. Okay. That's typically this general form, right? Okay. And often, at least for me, I'll write it like this. Okay, I'll use the second version of the equilibrium reaction and this equilibrium constant on the right. Okay, but this and use hydronium ions in your equilibrium and your equilibrium constant, and that's fine. Okay, I'm just again presenting it both ways in case you see it one way or the other in a book or on homework or things like that. Okay. All right. So, right, these equilibrium constants, right, we talked about, when we talked about chemical equilibrium, what the magnitude implies, okay? So what does the magnitude, right, imply in terms of the strength of the acid for these weak acids, okay? So a larger Ka implies what? That the acid is going to be stronger or weaker? Stronger, right? Because in this equilibrium reaction, right, so the larger Ka is, the more products I have, which means the more this acid dissociates and the more protons in solution, right? And the more protons you put in solution, the stronger the acid, the more acidic the solution is, right? So the larger Ka implies stronger acid, okay? Right, so the larger the Ka, the stronger that acid is, right? And therefore, the smaller Ka is, the weaker that acid is, right? So if I had a list of acids with their Ka values, I would list, and I asked what is the order of strength of these acids, right? You will list the acids in terms of the size of the Ka, which the strongest acid has the largest Ka, and the weakest acid will have the smallest Ka. Okay? Because again, these equilibrium constants tell us the ratio of products for reactants. And the more products we have, the more protons we have, the stronger the acid will be. All right. The next couple of problems, we'll talk about percent ionization, okay, of your weak acid. And that is just defined as the concentration that's been ionized over the original concentration, which typically is just the concentration of H+ ions at equilibrium. That's going to give you the concentration that's been ionized. And then the initial concentration is given of your weak acid. Okay? And that is the definition of the percent ionization and how we would calculate it. Okay? And so this first question here, right, we have niacin is one of your B vitamins, right? If I have, and it is an acid, okay, this, right? And so if I have a 0.02 molar solution of niacin, and I know that it has a pH of 3.26, question is what is the acid dissociation constant for niacin? That's that Ka, right? What is the value of Ka for niacin? And then what is the percent dissociation? Okay, that percent ionized. So that is kind of the next question in the example here. We're going to work this one out together from the beginning. Okay? So niacin here is a weak acid. Okay. So it has some Ka, right, that we're looking for, right? And it's a weak acid. I'm just going to think of it. Again, I'm not going to write out all of its structure. It's just some weak acid. So it's going to be something like Ha forming H plus A minus, right? Or again, I could go back to the slide and see the structure and the molecular formula, but it doesn't really matter, right? I know niacin is a weak acid, so it's just going to have that type of an equilibrium, right? Or Ha here, right? Ha is my niacin, right? Which I know is a weak acid, so I'll break apart into H plus and A minus. Okay? And again, the expression for Ka, the acid dissociation constant, okay, right, is going to be the equilibrium constant, or the equilibrium concentration of H plus times the equilibrium concentration of A minus, your conjugate base, right, over the equilibrium concentration of your weak acid, Ha. Okay? All right. So, right, this, right, is an equilibrium problem, right? I have some equilibrium reaction. It's this acid dissociation reaction. I'm looking for the equilibrium constant, given some information about the pH at equilibrium, okay? Right, it telling you that a 0.02 molar solution of niacin has a pH of 3.26. That's telling you that when you put this niacin in solution and it's equilibrated, you measure the pH, and that pH is 3.26. Okay? And so, given that, right, that it's an equilibrium problem, that I'm trying to relate my equilibrium concentrations to my equilibrium constant, right, this is going to require an ICE table. Okay? Where I have an initial concentration of 0.02 molar, right? Start off with none of my acid and none of the conjugate base. So I'm going to lose some amount of my weak acid, gain some amount of my hydrogen ions and my conjugate base. And at equilibrium, I'm going to have 0.02 molar, or 0.02 minus X. Sorry, 0.02 minus X of my weak acid and X of my weak, of my protons and my conjugate base, right? Now again, in the problem, you're told at equilibrium, doesn't say it in those words exactly, right? But it's telling you the solution has a pH of 3.26, right? pH equals 3.26, okay? And if I know the pH, then I know the concentration of H plus ions in the solution, right? Because the pH is just a negative log of H plus. So the concentration of H plus in solution at equilibrium, right, is just equal to 10 to the minus pH, okay? Again, this is one of those formulas, right, of converting between pH and H plus. They just need to remember, okay? So the concentration of H plus is 10 to the minus pH. And so this is 10 to the minus 3.26. Comes up 0.00055 molar. Okay? So that is the equilibrium concentration of H plus in the solution, which equals X, right? I'm given X, or I know the equilibrium concentration of H plus is X, okay? So, right, again, the equilibrium concentration of H plus equals X equals 0.00055 molar, okay? Which then I can plug in to my equilibrium constant expression, right? Ka equals concentration of H plus, which is 0.00055, times concentration of A minus at equilibrium, which is the same thing, X. So that's also going to be 0.00055, and then divided by the equilibrium concentration of my acid here, my weak acid, which is 0.02 minus 0.00055. Okay. All right. And I guess in some separate way, right? Plug those in, you get that your Ka equals 1.55 times 10 to the minus 7. Okay. So just plug it here. All right. Now, questions about this problem, right? Why did I do what I did? Where did this come from? Where did that go? Yeah. So what I knew I had to do an ice chart is I'm dealing with a weak acid, which in weak acid means I have some sort of equilibrium reaction, okay? Every weak acid has an equilibrium reaction. And then I also know I'm looking for the acid dissociation constant. So the acid dissociation constant is Ka, the equilibrium constant, okay? So the equilibrium constant for a weak acid equilibrium is called the acid dissociation constant. So if you see that word acid dissociation constant, that's referring to an equilibrium constant for that weak acid dissociation equilibrium, right? The weak acid dissociation equilibrium is HA breaking apart into H plus and A minus. And then again, and so it's asking for what Ka is. So if I have an equilibrium reaction and I'm trying to figure out what Ka is or an equilibrium concentration of something, then that's telling me I need to use ice chart. So that's Ka. And then, well, I guess before we do the second part of the question that I forgot about, other questions related with finding Ka? Class here on Zoom. So again, the other trick is, again, identifying the fact that the problem tells you that this 0.02 molar solution has a pH of 3.26, which is giving you information about what the equilibrium concentration of H plus is in this solution, okay? All right, and so to get the percent ionization or percent dissociation, didn't give myself enough room here, right? But the percent ionization, okay, or dissociation is equal concentration of H plus at equilibrium divided by the concentration of HA initially times 100. So that's going to be 0.00055 divided by 0.02 times 100. So that percent ionization here comes out to equal 2.7%. Okay. And again, for doing that, it's just remembering what that percent ionization is referring to. It's referring to the equilibrium concentration of H plus over the initial concentration of your weak acid. Okay. For the most part, we're not going to worry about calculating percent ionizations, but there's a point to doing it right now, and we'll get to that point after kind of the next problem or so. Okay. So. Any questions? All right, so let's do this next problem here, where I'm going to look for what is, right, so given the fact that the Ka of niacin is 1.5 times 10 to the minus 5, what is the pH of a 0.01 molar solution of niacin And then what is that percent dissociation? Okay. So again, here I know I'm dealing with niacin, which is a weak acid, so it has a weak acid equilibrium, right? And I'm given an equilibrium constant for this, which is 1.5 times 10 to the minus 5, which again equals H plus times A minus over HA, right? So I know this is going on in solution, and I'm asked for the pH of the solution. Well, the pH of the solution, again, is related to the equilibrium concentration of H plus. So I'm looking for what are the concentrations of these guys at equilibrium, which tells me to find the concentrations at equilibrium, I have to use my ice table. So I have 0.01 as my initial concentration of HA. I start off with none of my proton and none of my conjugate base. So I'm going to lose some amount of this, gain some amount of that, gain some amount of that, and I'll do 0.01 minus X, X, and X. Okay. So any questions about filling out this ice chart? Hopefully we're somewhat familiar with it, with all the problems from chapter 15. Okay. All right. So then if I want to find out, right, the equilibrium concentration of H plus ions, right, I need to solve for X, right? Because again, concentration of H plus at equilibrium equals X, right? That's what this line is telling me. The equilibrium concentration of H plus is X. Okay. So to solve for X, I need to plug into my Ka expression here. I have 1.5 times 10 to the minus 5 equals X times X over 0.01 minus X. Okay. Right. And so now when we look at this problem, say, great, we have some quadratic equation, we're going to have to use quadratic formula and such. But in the case for chapter 16 here, when dealing with weak acid and weak base dissociations, okay, weak acid, weak base is equilibrium, we can use a little trick, an approximation here, okay? And note, for example, in this previous problem, right, I had a 0.02 molar solution of HA at equilibrium. X was 0.00055. Okay? So if I look at, 0.02 minus 0.00055, right, that is 0.01994 or 55, right? No, 45. Okay, that's what that difference is, right? Well, if I round this to say the two significant digits, right? Round it to sig figs, right? This is 0.02, right? The concentration, the initial concentration for a weak acid changes very minimally, okay, when it's dissociation for a lot of these weak acids, okay? And so what I'm going to use here is I'm going to approximate this as 1.5 times 10 to the minus 5 is roughly equal to X times X over 0.01. Oh, sorry, that's not on slide here. Okay, so this is an approximation. Okay, right. I've made an approximation that 0.01 minus X, basically 0.01. Okay, that is an approximation, but it's going to be a very valid approximation for these problems. Okay, and we'll talk about the validity of that approximation in a minute. Okay, but if I do that, I then multiply 0.01 on the other side, so I get X squared equals 0.01 times 1.5 times 10 to the minus 5. And then so then I just take the square root of both sides of this equation to get the X, which is that equilibrium concentration of H plus is equal to 3.87 times 10 to the minus 4. Okay. And so now I have the concentration of H plus. To get the pH, I take the negative log of that, right? pH, negative log H plus. And so pH is equal 3.41. Sorry, it's kind of crammed in there, but pH is 3.41, okay? Given that the concentration of H plus is 3.87 times 10 to the minus 4. Questions about this problem? And so I'm going to calculate the percent ionization here. Okay. Right. That percent ionization for this problem. Sorry. Trying to see here. Just fold this over. Right. So I can try to fit everything. Right. So the percent ionization, right, is again the equilibrium concentration of H plus. So that 3.87 times 10 to the minus 4 over my initial concentration of 0.01 times 100. And so this percent ionization equals 3.9%. Right. And in that first problem, the percent ionization was 2.7%. Okay. And so right, this last question here is compare the percent associations for the 0.2 and 0.1 molar solutions, right? And so for the concentration of HA here, the niacin equaling 0.02 molar, percent ionization was equal to 2.7%. And for the concentration of HA equaling 0.01 molar, percent ionization equals 3.9%. Okay? Right. And so we see as the concentration of your weak acid decreases, its percent ionization is going to increase. Okay? So as the concentration of your weak acid decreases, the percent ionization, the percentage of that weak acid that breaks apart in solution increases, right? So the less acid you have, the larger percentage of it is going to be breaking apart into solution. Okay. And then I want to note that all these percent ionizations are relatively small, 2.7%, 3.9%, okay? When the percent ionization is less than, I'm trying to remember what the rule of thumb is, like 5 to 10%, I think typically 5% or so, but percent ionization is less than like 5%, okay, 10%. This approximation that we used up here is more than 5. Now in lab, I think they have a different kind of rubric that they use to discuss kind of when this approximation works, okay? But, all right. But if we want to verify that our approximation is valid, we calculate this percent ionization and see that's less than like 5 to 10%, okay? And then we'd say, okay, this approximation is going to work out just fine, okay? Right. Which in this class, you aren't necessarily going to need to calculate the percent ionization to say the approximation is going to work. You can just use that assumption, that approximation, okay? Right. I think what? Another thing that's done, I'm trying to remember in the lab, I think last year someone told me about it. Something like comparing the concentration of your acid to the equilibrium constant Ka, And when the ratio of those things is different by a factor of like 100 or 1,000 or something, then this approximation works fine too. But so there's different kind of rubrics, different ways that you can kind of, check to see, can I assume that my initial concentration of my weak acid minus the change is just basically equal to the initial concentration, right? That is our approximation. That change is so small that roughly the concentration of our weak acid isn't changing in the solution, okay? Again, if I were to round to my significant figures, right, that's what I would see, okay? And again, that approximation works out just fine for most problems. Okay? And any problem really that we're going to be dealing with, like on a quiz or on an exam or something like that, you'd be able to use that approximation and not worry about it. Okay? So questions about these examples of calculating pH or Ka, right, for some weak acid, given different information here. Okay. It's a very common problem, and again, a problem we will deal and use quite a bit in this chapter and as well in chapter 17. So we'll see this again and again. All right, and again, how we approach these problems is we say, okay, I'm dealing with a weak acid. That means it has a weak acid equilibrium, this weak acid dissociation equilibrium, right, that has an equilibrium constant, A, of the H plus ion with the conjugate base over the weak acid, okay? I know then I'm going to be needing to use some sort of ice table to relate initial concentrations and equilibrium concentrations, and then I'll use that ice table in my definition of my equilibrium constant Ka, this acid dissociation constant, to try to find out, say, what are my equilibrium concentrations in solution. Okay? And then we'll often use this approximation that our initial concentration of our weak acid minus the change is negligible, and so I can just use the initial concentration here to solve. Okay? And then it makes doing the math a lot easier, right? No quadratic formulas or things like that. You've got to take the square root of some number. So again, questions? So did those? Okay, so only other type of acid we have not talked about in great detail, we've shown some examples of it, I haven't really talked about it, are polyprotic acids. So what is a polyprotic acid? It is an acid that has multiple protons that it can donate to solution. For example, here, this H2SO3, HSO3, right? So H2SO3 is a polyprotic acid. It has two protons that it can donate into solution, right? As an equilibrium reaction for that first proton, and then an equilibrium reaction for that second proton, okay? Once it's donated the second proton, right, it's got no more protons to donate to solution, right, so it's done, okay? But this acid here, H2SO3, has two protons it can donate to solution, so it is considered a polyprotic acid, and it's not going to donate those two protons at the same time. It will do it one after the other, and we will have two separate equilibrium reactions that get established, okay? And we use these little notations here, Ka1, Ka2, to indicate the first proton that's donated, and then the second proton that's donated, and so on and so forth, right? So for example, right, for Ka3, for phosphoric acid, okay, phosphoric acid is H3PO4, right? So Ka3 is asking for the equilibrium constant for the donation of the third proton to solution, which means my phosphoric acid is already donated 2. So start off with HPO4 2 minus, going to H plus PO4 3 minus, okay? And the equilibrium constant for this reaction is this Ka3, because again, the 3 here is telling me I'm looking at the equilibrium constant for the donation of the third proton, right? I already donated 2 protons. Compare H3PO4 to HPO4 2 minus, and we see, right, that I've lost 2 protons. I lost 2 hydrogen atoms here. And this equilibrium constant, right, is then just concentration of H plus times concentration of PO4 3 minus divided by concentration of HPO4 2 minus. Okay. So that is the acid dissociation equilibrium constant for the third proton that is donated from this polyprotic acid that is phosphoric acid. Okay. Right, so that is what those Ks are referring to, okay, K1, K2, and then note that the Ka values get smaller and smaller for each successive proton that you're donating, because it gets harder and harder to remove the protons as you keep on removing more and more protons, right? Right, you see here H2SO3 is fairly happy to give up its first proton, right? Equilibrium constant 1.7 times 10 to the minus 2. Still kind of a small number, but not that small, right? But then I get to the second proton here, where I take HSO3 minus and try to donate another proton to form SO3 2 minus. And that has an equilibrium constant, right, of 6.8 times 10 to the minus 8, which is a fairly small number, right, telling you that this really doesn't want to form products, right, and it's not very easy to remove that second proton, okay? And again, the general trend is it becomes harder and harder to remove the protons after each proton is removed in a polyprotic acid. Questions about that? Polyprotic acids, weak acids. All right, so the last thing we'll need to define, right? We'll try to find a strong acid, strong base, weak acids, polyprotic acids. Last thing is our weak bases. Okay? What would be the definition of a weak base? Right. The strong base is a base that fully dissociates in solution. A weak base will be a base that partially dissociates in solution, right? Right? And often they will establish some type of equilibrium. Now, the equilibrium could be something like this, where you have some base plus water forming some conjugate acid plus OH minus, okay? Right? Other potential examples, right? So, often you'll also see kind of me writing this base dissociation reaction for some weak base as, say, A minus plus H2O, forming HA plus OH minus, which again then has an equilibrium constant. This base dissociation equilibrium constant, right, is going to be concentration of HA times concentration of OH minus over concentration of A minus, okay? Note here, right, that I'm not including water, right, because water is just a liquid, right? It's not included in your equilibrium constants, okay? And why often you'll see it kind of written like this is because often a lot of the weak bases we deal with are conjugate bases of weak acids. So for example, fluoride ions, F minus, acetate ions, CH3, COO minus, I don't know, nitrous ions, NO2 minus, okay? These are examples of weak bases, right, which happen to be conjugate bases of a weak acid, okay? And we'll talk more about the relationship between conjugate bases and conjugate acids, of weak acids and weak bases next time, right? But, okay, but so often, right, these weak bases then undergo this type of an equilibrium reaction where it will react with water to form a weak acid and OH minus, right? So for example, F minus, right, will be F minus plus H2O, forming HF plus OH minus, right? That would be the weak base equilibrium reaction, okay, that has a equilibrium constant that's given by Kb, okay? So like the weak acids, where the equilibrium reaction has an equilibrium constant that we call Ka, to indicate this is for weak acid dissociation reaction, okay? For bases, call it Kb, right, for weak base dissociation reaction, weak base equilibrium reaction, okay? Right. So again, a weak base only partially dissociates in solution. We'll have this type of an equilibrium, okay, in solution. Right. Right. And so, for example, we're going to do this for ammonia, okay, and acetate, right? So we want the equilibrium reaction for our weak bases, ammonia, NH3, and acetate CH3COO minus, right? And again, these weak bases, right, will react with water to take a proton from that water, right? Because these are acting as a base, so they need to accept protons, right? So the proton has to come from somewhere. That proton comes from water, right? Weak acids, the water doesn't appear in the equilibrium reaction because the weak acid already has the proton to donate, right? But a base doesn't have the proton to accept, right? It's got to get that proton from somewhere else. It's going to get the proton from water in these equilibrium reactions. This is going to form NH4 plus OH minus, and this one's going to form CH3COOH plus OH minus, right? So these are equilibrium reactions. We're going to have KBs, right, equal to NH4 plus OH minus over NH3, and KB equaling CH3COOH times OH minus over CH3COO minus, right? Again, these equilibrium constants, right, just follow the same set of rules as your equilibrium constants for any equilibrium reaction, right? Products, overreactants, rates of their stoichiometric coefficients, okay? Ignoring liquids and solids, right? Water here, again, I typically don't bother writing a lot of these phases, right? But water is a liquid. Everything else here is an aqueous ion, okay? So water doesn't appear in the equilibrium constant. Everything else does, right? And so those are our reactions for these weak bases, okay? As well as then their equilibrium constants. And again, what is a weak base? It's something that partially dissociates in solution, and it's basically any base that is not a strong base, right? Which all of your strong bases are your alkali and alkali earth metals, okay? So any questions about definitions of weak bases, weak acids, polyprotic acids? All right. So we will end things here and pick up with doing some more of these examples on Monday. Okay. For those in class, don't forget to turn in your participation questions on the back table. Remember, question number 3 is asking which solution is more acidic. Okay. When you're trying to answer question number 3. Any questions from those here on Zoom before I close out the session? All right, don't see any questions here, so I will close out the Zoom meeting and see you guys on Monday.